forces reassessment. We have a block that weighs 5 kilograms being pulled up at an angle of 15 degrees, and it's on a slope of 35 degrees. Here's my free body diagram, and we know that for this, which is going to be our theta 2, cosine of 15, and then we know that for this, which is our theta 1, 35 degrees, it's going to be sine of 35. Alright, and at rest, f net of x equals 0, and f net of y equals 0, and it equals tension times the cosine of theta 2 to get our x, and f net y equals mg sine theta 1, because it's going to be mg pulling down, and our sine of theta 1 to get to this, our y. And then finagling those formulas around to equal each other and subtracting, we get t cosine of 15 degrees minus m times g sine of 35 degrees equals 0. And t times cosine of 15, we just added the mg sine 35 to each side, and we get t cosine of 15 equals mass times gravity times sine of 35. And then solving for t, we get t equals mass times gravity times the sine of 35 over the cosine of 15. And plugging in our numbers to get t, we get 29.1 newtons. The second part of the problem I added in was if we change the second angle from 15 degrees like it was in this first part to 5 degrees, would the tension be larger or smaller on the rope pulling the block? So, setting up our problem the same way we set up the first one, we have f net of x equals t cosine of 5 degrees minus mass times gravity times the sine of 35 degrees equals 0. Adding mg sine 35 to both sides, we get t times cosine of 5 degrees equals mass times gravity sine of 35 degrees. And then solving for t, dividing by the cosine of 5 degrees, we get t equals mass times gravity sine of 35 degrees over cosine of 5 degrees. And plugging in our numbers, 5 kilograms for the mass, 9.8 newtons per kilogram for gravity. And we have sine 35 over the cosine of 5, we get 28.2 newtons, which, that's for our tension, which is less than the tension at 15 degrees. So our answer is tension is less than.